All right, hey guys, welcome to today's lecture on recursion. Um, so I checked the Slack and it doesn't seem like anybody wants a review. Um, so I'm gonna just go ahead and jump into this lecture if that's the case. Uh, so yeah, let's get started. All right, so recursion is a topic that is confusing to almost everyone when they first start out learning it because it introduces a new way of thinking about solving problems. And because of that, it's difficult, but it's also very valuable because of that as well. So today we're going to learn some of the foundations so that we'll be able to understand what recursion is and what's actually happening, what your computer is actually, or your program is actually doing, and how it keeps track of where it is. And basically, we'll learn that recursion, which is defined as when a function calls itself, it's not that much different than if a function were to call a different function. It's the same idea, but it just happens that it's calling itself instead of a different function. And then we'll go over some examples to really hammer it home, and then we'll learn through some exercises. And I'll give you guys some tips on how to approach specific problems using recursion. And we'll learn that there are patterns that we could utilize where it'll help us to solve like 80% of the problems, 70% maybe. The 30%, it'll be really tricky and they're made to be super challenging. But for 70%, I would say, of the beginning level recursive problems, you could apply this concept and have this framework and the strategy, and then you should be able to handle like the majority of them, or at least get started, know where to start. Give me 1 second. So recursion is basically when a function calls itself. And we could think, it can be used as an alternative to a loop. So for the most part, every problem that you could solve with a loop, you could also solve with a recursive approach. So why would we even learn about recursion? Well, number one, it's a popular interview topic, and a lot of companies like to see if you are able to grasp it. It sometimes is easier to read than an iterative solution because it's less code. Because if you think about it, you're using the function, you're like really squeezing every single drop from that one function. So we've talked about the concept of helper functions, creating new functions to help you break down the problem, right, into smaller parts. So we did, back when we had to iterate over all those crazy nested objects, we created a helper function that did one thing. It operated on one part of the object, and then we created another function that like iterated and called that helper function on each small part. But if you guys were trying to follow my code, you would have noticed that it's a lot of code. I'm creating new functions. I'm writing a helper function, and then I'm writing the helper function's wrapper function, and then I could even go another level, so that I'm writing a lot of code and creating a lot of different functions. Whereas recursion, it's not simple, but it's very descriptive, and it's very powerful because it's just one function, and you're using it kind of like a helper function, but you're using itself. So it's, in the end, it's, if your function is 10 lines or 5 lines, that's all you have to write, and you're using it multiple times. Also, it introduces a new way of thinking about problems. So if we were to ask sum all of the items in an array. Let's say you had an array and we had to add up all the elements in that list. The conventional way to think about it is go use a for loop and loop through each element and then add it to an aggregate sum. But that's thinking about the problem holistically, like the entire problem at once. Whereas for recursion, we could start thinking of problems like this, like breaking it down into its simplest part. So for example, let's do a little code example. So a simple way to think about summing all of the elements in an array is we have this array, right? And then basically the normal way to think about it is like go through each element in this entire array, iterate through and add them to a sum. Whereas a recursive approach might be, take the first element and add that to the same function, but call that on a smaller part of the array. So it might be like sum equals sum equals array 0 plus sum of array dot slice 1. You're using the same function, and then you're just breaking it down into a smaller part and then calling that same function on a smaller piece of that versus just using a for loop. So it's kind of like a different way to approach things. And we'll get more practice into this. If this was confusing, it's okay, but it just goes to show that there's different ways of thinking about how to solve a problem. You could tackle the whole thing at once, like I'm gonna tackle the entire array, or you could just say, I'm gonna tackle, I'm only gonna pull the first element out, and then I'm gonna tackle the remainder, because I could run the same function on the remainder, and it should still give me a sum. Like if I could sum an array of 5, then I should also be able to use that same function on an array of 4, also that same function on an array of 3. And so it uses that logic of, if I could use my function to solve a really big problem, I could use it to solve smaller and smaller parts of that problem too. It can be a performance hog. We won't talk too much about performance, but because when we introduce the concept of the call stack, essentially recursion doesn't allow, it keeps all of your function calls in memory in a call stack. And so it can be a memory hog because it needs to keep the separate function calls in memory. And we'll see that a little more in depth in the next slides. But it really simplifies certain complex activities like traversing data structures, traversing trees. These are all, you could do it iteratively, but using the recursive approach is a lot easier on the eyes. And we'll see some examples of this. So before we talk about recursion, we have to talk about the call stack. So essentially the call stack is a mechanism, it's a manual that JavaScript uses to see where in the program it is. It's how it keeps track of what it's doing, what it has to do next, and it's the way that the program knows where it is. And so we could think of a stack like a stack of books or a stack of pancakes, and that's why they call it a stack. Essentially, we'll look at the call stack here. We could just imagine it like a stack of pancakes, for example, and when we call first, when we invoke this function on line 12, then that gets placed onto the call stack as our first book or our first pancake. And then when that function is done running, it gets popped off the call stack. And so here we put, first on the call stack, and now JavaScript knows I'm running this function. This is where in the program I am. I'm running first. And then it'll put console log, because console log is also a function, but it won't see it now. We won't see it now, but it'll, do its thing. It'll run the code inside of it, line 5, and then it'll pop it off the stack because we're done with that function. So it gets popped off the stack, and then we add second, because first is done now, so we add second to the call stack, and second is the same thing. A little log I am second up here, and then it's done running because there's no other line of code to execute, so it's done running and it pops off the stack. So how about something like this? Wait, what happened here? Okay, so this one is a little trickier, but first we add first to the call stack, since that's the function that's being called right here on line 11. And then what do you think? Does anyone want to take a stab at what happens next after first gets placed onto the call stack?
First run, I am first.
Yeah, it runs I am first, exactly. Great. And then what happens after that? After we log I am first to the console? Yeah, Anderson says second gets placed on the stack. Yep. We can't pop first off because first is not done running. We're still in the middle of running first. So we can't remove it. So, but then before it's finished, it calls a different function. So now JavaScript needs to say, okay, I'm not done running first, so I'm going to keep it in the call stack because I'm not finished with it. It's like you're eating a pancake and then you ate half of it, but then your mom gives you another one and it puts it on top of that half-eaten pancake. So you can't really clear the plate. You have to start working on your second pancake now, which is like whole, right? So it places it on top because first is not done running, and then we run second. So we go to line 8, and then we log I am second, and then now what do you think happens? Any guesses?
Second run.
Yeah, second runs. So it logs I am second, and then what happens after it runs?
It finishes, sorry.
And then what happens when it finishes? Like what happens in terms of the call stack? Yeah, cool. So Anderson says it gets popped off. Second gets popped off because we're done running second now, right? Here's the thing. We can't pop first off the call stack until second's done running. The completion of first hinges on the completion of second. Like if second never finishes, then first will never finish because it can't go to line 4. So second, it's like if you were eating pancakes and you ate half of the first one and someone put a second one on top, you have to finish that second one before you go back to the first one. You can't just flip it over and then start working on the first one again. You have to finish that second one that got placed on. So then second gets popped off, and then now first can continue and hit line 4, and then we run first finished, and then first gets popped off. So this is what's happening. This is how our computers or our program knows where in the program it is and like what function to run next, what function it's currently running, what function to go back to when the current function is done. This is kind of how it manages all of that in a data structure that's relatively simple. It's just a stack. Uh, and by stack, we mean it's kind of like an array, where you can think of it as an array where we could only push and pop. We can't do the other unshift or shift like the other methods of an array. You could only push into an array, and then you can pop off the top of the array, which is basically what happened. We pushed first in, and then we pushed second in, and then we popped second, and then we popped first. So you can just think of it as that kind of data structure. And we'll see that in recursion, it's not, if we think of this call stack structure, then it kind of makes a little more sense, because in recursion, instead of first calling second, it just simply calls first. So first puts itself on the call stack, and then it puts itself again on the call stack, and then it puts itself again on the call stack. So that's sort of like what recursion is. We could just think of replacing second with itself, but we'll get to that. So now let's try and take a stab at writing a recursive function. So this is one way we could do it, right? If we wanted to make a function that can count down from a number to 1 without using a for loop, because we want to use recursion, then this is kind of close. We're kind of getting there, because we just manually create this function countdown, and then we call countdown 5, countdown 4. We like write this ourselves manually, and that accomplishes the task of getting from 5 to 1 without a for loop. But notice how we're limited here, because we have to hard code these ourselves. Like, we can't dynamically put in 8 or 9. Like, if we want to count down from 500, we can't just sit and type countdown 500, countdown 499, countdown 300, 498, 497. We just make the computer do that same thing. And how we're going to do that is basically using recursion. So instead of manually calling countdown, we could have countdown call itself, subtracting 1 from the number each time. So if we want to take a look at what happens here, is we call countdown 5, right? And then that will place countdown 5 on the call stack. I think there's a call stack. Yeah, perfect. So we call countdown 5. That places countdown 5 on the call stack, right? And then we start running it. So we run console log 5, and that logs 5 to the console. And then here's the tricky part. We call countdown 4, because we do num minus 1, and we call countdown 4 again. Notice we can't pop off the call stack because we're not done running. So countdown 5 isn't technically done running until countdown 4 is done running. So we put countdown 4 on the call stack, right? And then what do you think will happen after we put countdown 4 on the call stack?
Countdown 5 stops running, and then 4 starts running.
Yeah, exactly. So what happens when 4 starts running? What will it log to the console? It'll basically log 4, right? Because now we're running countdown 4, so it's gonna log 4 to the console. And then what do you think will happen next? We're in countdown 4, it logged 4, and then it calls countdown 3. So what happens? Yep, on the stack, we put countdown 3 on the stack, and then we log countdown 3, and then countdown 3 calls countdown 2. Notice, like, we're never popping, we're only pushing, and that's generally not a good thing to do, because when we're constantly pushing and never popping, we're gonna run out of memory, because each of these rows that in the stack takes memory. Like, the computer needs to allocate a specific piece of memory and say, like, oh, this is this function that's running, so let me allocate it here, and then once it's done running, I can remove it, because the function's done and I don't need to keep track of it anymore if the function's done running. But here it's never finished because countdown 5 never finishes until countdown 4 finishes. Gets stuck on line 9. Unfortunately, countdown 4 never finishes until countdown 3 finishes. And unfortunately, countdown 3 will never finish until countdown 2 finishes. Can anyone see a problem here? Like it never ends. Like it never stops running because we're constantly calling itself. It's almost like a for loop without a constraint, like a top constraint. It's like a for loop without adding the middle argument. Like you're never getting closer till the end. Or yeah, it's essentially a for loop without the middle argument that tells it when to stop. Or essentially it's a while loop that the condition is like always true. Like it never stops running. And this is the same case. It never doesn't call this function. Like we need some case where it doesn't call this anymore, because if we keep calling it, then we'll never be able to pop off the stack. It'll never finish running. So it'll keep going on and on and on and on and on. And then it'll give you stack overflow error here. Maximum call stack size exceeded, meaning the program doesn't have unlimited resources and it can't just forever be calling this function because, you know, it's taking up too much space at this point. Does anyone have any questions about that? It's a pretty important concept to understand. Is in recursion, you always need a case where you don't call the function. Like it wouldn't be recursion if you didn't call the function. So you do have to call the function, but you need some type of case or conditional where you don't call it anymore. And so how does anyone want to guess like how we might do that in this function, how we might change this so that it yeah, so Nathan says an if statement, it's perfect. So we need a stop condition. Yeah, so the computer runs out of memory, and then we need a stop condition so the function eventually stops calling itself. Okay. Yeah, so it's simple as running a console log. And then else in the recursive call, we just call it. So here's our base case, our stop condition. This is sometimes referred to as the base case. And then we also have the recursive case where we actually call the function itself. Notice two things here that are really important. In your base case, don't call the function again. You need to do anything except call the function again. Because now, when we run line 4, the function is done. It can finally be popped off the stack because it's not calling any other function. It's not waiting for that function to complete. So after line 4, the function is done. It is out. And once that function is done running, whatever function was dependent on that function, it's like a chain reaction. Like if countdown 2 needed countdown 1 to complete, and countdown 1 completes, then countdown 2 is now completed because countdown 2 depended on countdown 1 to finish. And once countdown 2 is completed, countdown 3 can also be complete and popped off because countdown 3 was dependent on countdown 2. So it's like a domino effect. Once that last function call returns, everything before that was dependent on that can get popped off the stack, and then we're free. It's exactly what we're looking for here. And so because of that, that's one thing to note. Always in this base case, do not call the function. Second important thing to note is in your recursive case, you need to get closer to the base case. So notice how we're constantly decrementing by 1 here. So we're in our next iteration, if we call countdown 5, it'll call countdown 4. And then it'll call countdown 4, will call countdown 3. And each step, we're moving closer to this base case. And so that's another important thing, because if you don't move closer to the base case, like if countdown 5 just calls countdown 6, if we did a +1 here, and then countdown 6 calls countdown 7, and then countdown 7 calls countdown 8, we're never going to hit this case. So we eventually do need to hit this case. So important thing number one is have a base case. And important thing number two is in your recursive call, get closer to the base case. So I think there's a call stack example here. So yeah, countdown 3, calls countdown 2, and it calls countdown 1. And countdown 1 calls countdown 0. Now, what's the interesting thing that happens here? Anyone want to take a stab at it? Once countdown 0 happens, what will happen when this function gets called with 0?
It breaks.
Yeah. It completes, because we get into this conditional if statement, exactly. So then we log done, right? And then what can happen now when that function's done running? Yep, call stack pops off. So 0 pops off, right? And here's the interesting thing. Countdown 1 is at line 11. Like this function call, countdown 1, is stuck at line 11 waiting for countdown 0 to be done. And we just finished countdown 0, which is amazing because countdown 0 is done. Countdown 1 was at line 11 until it's done. So once countdown 0 is done running, then countdown 1 is also done, because countdown 1 was stuck at line 11 waiting for countdown 0. It was like, hey, are you finished yet? Are you finished yet? It asks him, are you finished? And countdown 0 can say, yes, I'm finished because I'm done running my code. At line 6, I'm done. And countdown 1, it finishes at line 11 because it was dependent on countdown 0. And so now countdown 1 can get popped off. Countdown 0 gets popped off. But by virtue of the fact that 0 gets popped off, it could pop everything off, because now countdown 1, which is dependent on countdown 0, is done. And then now countdown 2, which was dependent on countdown 3, or countdown 2, which is dependent on countdown 1, is also done, and so on. And so it's a effect that essentially, when you have a stack of dependencies, it's literally like a domino effect. Once countdown 0, falls, once it's done, it tells countdown 1, like, hey, I'm done, by hitting it like a domino. And then countdown 1, while it's falling, it hits countdown 2, telling countdown 2, like, look, I'm done. Let me tell you I'm done by hitting you and knocking you down. So then whatever dependencies that you have will all get knocked down eventually, like one by one. And that frees up the memory. And so you don't get a Stack Overflow error. And look, it's beautiful. We solved a problem where we'd normally stick to iteration by using recursion. So yeah, these are the two takeaways. And it's important to think about them when we're creating a recursive function, is having a base case. So let's think of a case where we can just solve the problem. And usually this is the simplest case. So for example, let's go back to this problem right here where we had an array of, let's see, what's something that we add up, array of sales, right? Let's say we had a bunch of sales and we wanted to add it up, so one day we made $100, next day we made $500, next day we made $200, next day we made, it was a tough day, so we made $21. So how are we going to add all of these? Recursively, right? So the simplest thing to think of is, and we could take this from the countdown example, is let's define our base case. And for our base case, we could just say, let's solve the simplest case possible. That's why I do enjoy recursion, because usually you're always able to at least get started by saying, what's the simplest version of this problem? And we could say, what if our array was only length of 1? Like right now we're trying to solve this long array of 4 elements using recursion. It's kind of hard. Like, where do we even start? Like 4 arrays. Like, I don't know what to do. But what if, what if it was just one number, right? Then how do we get the sum of, oh shoot. Not sure what this is. Let me check. Crashed. Okay, so the simplest array, we could even say array of 0, but we'll just, for our purposes, try to add sum an array of length 1. Like, how do we do this? Don't even think about this array of length 4. Like, how do we solve a array of length 0 or length 1 for that case? Is basically we would just return, array of sales 0, right? That would just be our sum essentially. And so that's how we could kind of, and I'm not going to solve this right now, but that's kind of the first approach. And then we kind of call the sum function on array, like everything after that element, so that, we do 100 plus sum of this array. And what's the sum of this array? It's 500 plus the sum of this array. And what's the sum of this array? It's just 200 plus the sum of, so it's like taking the simplest version of a problem and then solving that, and then handling the rest of it in your recursive case by, shortening that element by, usually by 1. So that's kind of like the approach here is like, we could console log. I mean, this in this example, it's not quite the same, but that's the kind of, and we'll, see it in the next example that's a little more complex. But here we can just think of, oh yeah, our simplest case is like our number is 0. Like, what happens when our number is 0? Like, we just don't even console log the number. We just console log done. And we don't call, like, we're done at that point. It's our base case. So we don't need to console log any other number. And so that's like our simple case, our most even trivially seemingly trivial basic case. We want to solve that first because usually that's our base case. And then our recursive case is just going to be calling, that same function, but just passing in a piece of the parameter that's like broken down by 1, like getting it closer to our base case. So returning from recursive calls. So here's where it gets a little more interesting, is when our recursive calls return. So before we weren't returning anything, we were just logging here into the terminal. But what if we need a return? Like, how would we handle that? So again, we need a base case, and base cases often occur when there's a simple input that expects a simple output. So here, for the example of a sum, the sum of, an array of 1 is just that number. So simple input to simple output, that's usually our base case. So we want to test that the base case works before working with the recursive case. So even for even if it seems trivial, like we'll just say, function recursive sum takes an array, right? And we'll say if array.length equals 1, return array 0. That's it. Before we even do the recursion, we want to know that our base case works. And so we could say, just test that out. So console log recursive, and it's not really recursive right now, but it's you'll find that this is like a big step to solving the problem, is just solving the simplest version of that problem. And then once you have that solution, then it kind of the next step is just a little bit of a reach away. So just test that it works on the simplest outputs and inputs. And then, yeah, now we'll go through an actual example. So if you guys are curious about this one, it's basically else return array 0 plus recursive sum of array dot slice 1. I think this will work. 500, 221. Yeah. So basically what I'm doing is like, I'm returning, you know, if it's only of length 1, then I'm returning this. If it's greater than 1, so if it's 2, I'm returning the first element plus I'm calling the same function on a smaller part of that. Because ideally, if my function works for array size of 3, it'll work for array size of 2, it'll work for an array size of 1, right? So it's kind of like, here's our base case, and then here's our recursive case where we're actually calling the function, but we're getting closer to the base case because each time we're slicing the first element off the array. And so the array size is getting smaller each time, and we're getting closer and closer to having the array length to equal 1, which is our base case. But yeah, and this is kind of a pattern that is similar for handling arrays and strings and things like that, but let's go over this example first. So a factorial is basically when we multiply that number times 1 minus that number times 1 minus that number times 1 minus that number all the way up to 1. And so our base cases, does anyone want to take a stab at what our base case might be for this case? So, you know, if factorial 5 is 5 times 4 times 3 times 2 times 1. Factorial 4 is 4 times 3 times 2 times 1. Factorial 3 is 3 times 2 times 1. What are our base cases? It looks like we almost have 2 base cases here. It's basically when our inputs are, yeah, exactly. So Ranfi says if num equals 1, return 1. And even to 0, so we could even put this in as well. So if the input equals 0 or 1, then we just return 1. It's almost like a given, like just like how you know, if the array length is 1, just return that element. It's this is just a different method. It's more of a mathematical rule where factorial of 0 is just 1. It just is. That's just the rule. And then factorial 1 is also just 1. That's also just a rule, just like how 2 plus 2 equals 4. It's just one of these mathematical rules that we could leverage as the base case. So here we are. We're off on the right track here, because trying to solve this in a recursive manner, we're essentially creating our base case right here. And then it'll work for 2 inputs, which is, you know, a huge win. If there's 2 test cases already passing, because this is our base case. Now, how do we get to our recursive case? So there's a little pattern here where essentially factorial of a number is that number times factorial of that number minus 1. So it's kind of a pattern that we could utilize for our recursive approach, where essentially 2 times factorial of 1, so 2 times 2 minus 1 equals or 2, yeah, because factorial 1 equals 1. So 2 factorial is 2 times 1. 3 factorial is 3 times factorial of 2. And factorial of 2 we know is 2 because we're just manually solving it here. So, factorial 3 is 6 because it's 3 times 2. Factorial 3 is 6. Factorial 4 is 4 times factorial 3. So that becomes 24 and so on. And so it's just important to notice this pattern where a factorial of a number is that number times the factorial of the number before it. And this by nature is recursive because we're utilizing the same function to solve different versions of that function with different inputs. So here's our base case again. Now in our recursive case, we need the number to get closer to 0 or 1 somehow, right? Because let's say we had factorial 5. Then we need to somehow call factorial 4 because it needs to get closer and closer to 0 or 1 so that we could get that first domino to fall, thus triggering all the other dominoes to fall as well. Because if we picture our call stack, we have factorial 5, which calls factorial 4. Which keeps stacking on, and we need that trigger to start popping things off the stack. So let's start with a really simple case of factorial of 2. Once we have our base case, we don't have to get crazy, right? We don't want to start trying to do factorial of 100. We'll just try doing factorial of 2. So if the num was 2, if we had factorial of 2, does anyone want to take a stab at what we would place here if to try and solve factorial 2, knowing that factorial 2 is that number times factorial 1. So how would we solve factorial 1? We don't have to do anything because it falls into this conditional, it'll just return 1. So Liz John puts exactly, so it's num times factorial num minus 1. That's perfect. So let's just try it out right here, right? So we have factorial, and that takes in a num. And our base case is if num is 0 or num is 1, then we return 1, right? Else, and Liz, you said num times factorial of num minus 1. This is really good. It's very close. But does anyone want to guess what happens when we call this? Any guesses? So Liz, I think you're onto something. You have to add it too. So, and Anderson puts 1. So essentially you'll get undefined, I believe. And that's because, so yeah, you guys are all on the right track. It's, so if you do num, so Liz put num times equals factorial of num minus 1, right? But that'll still be undefined.
Yeah, I'm realizing you need a new variable to store the sum in?
Or... Close, but I'm thinking of initially it was just as simple as this, but then we just need to return that. And now we should be getting 2. And basically what's happening here is, let's just draw out the call stack. So we have factorial, we call factorial 2, right? And so that puts factorial 2 on the call stack. This is our call stack. And then what happens when, so essentially we're saying return num, or to make it a little less confusing, we'll say let result equals num times factorial num minus 1. And then we just return result. So just to make it a little less confusing, so it's not on the same line. But essentially what happens when in our call stack, factorial 2 is placed on the call stack. In factorial 2 runs line 5, right? And it says let result equals 2 times factorial of 1. And so now we're calling factorial 1 before we're done running, before we hit line 6. We're not done yet. So we have to call, in our call stack, we call factorial 1. And factorial 2 is still there on the call stack. And so factorial 1 goes to line 3 and it just returns 1. So this essentially becomes interchangeable with 1 now. Like factorial 1 has become 1. Like it became the number 1. So now factorial 1 is done running, right? Because we hit this and we've essentially returned. The difference between console log and return is like now console factorial of 1, like this becomes 1 because I've returned, right? Before, like if I just did console log of 0 or 1 or something, then this would also not work because factorial of num minus 1, which is factorial of 1 in our case, in our current example, right? It's 1. Like num is, this input becomes 1 because num is 2. So it calls factorial 1. And in factorial 1, it'll log 1 to the output, to the console, but it's not gonna, this function call is not able to be interchanged with that value anymore because we're not returning from here. We're just logging. So this result essentially becomes num times undefined because we're done running this. So this actually gets popped off the stack, but this value is undefined. So we're going to essentially return undefined times times 2, which like I don't even know what it is, but it's not the right answer. So because we did a return of 1, now both of these finish the function, you know, right? Console log 1 or return 1, they both complete the function no matter what line of code you run. It completes it because if there's no line of code after it, then you're done running the function. But the difference is that line of code where you actually called that function will become the return value if you return. Otherwise, it's just going to be undefined. And then that's going to throw a wrench in things because if you have an undefined and you're trying to like add to it or subtract from undefined, it's just not going to work. So here we return 1, right? And so when factorial 1 gets called, it returns 1. So it's done running, right? We can pop it off the stack. But here's the cool part is now this becomes 1 because factorial of 1 returns 1. So when it's done running, it passes that value, that return value, to it like transforms itself into that value because it returns it. So now it's perfect because now, you know, now we're back to factorial 2 because factorial 1 just got popped off the stack. It's done running. So now we're focusing on factorial 2 again in the call stack. Factorial 2 can complete line 5 now because this is 1. It's not a function call. So now we just do 2 times 1 and then we just return 2. And that should be it. factorial of num minus 1. And so that's the difference between returning and not returning, is that they both pop off the call stack. So no matter what, even if you did console log here, it wouldn't give you like a stack overflow error, because you're still finishing that function. So it console logs 1, but then our actual output of the function call is nan, because we're doing undefined times num. So that's the difference between returning and not returning. So let's dive a little bit deeper and see if there's any more slides that address that call stack example. So yeah, here it's saying it's undefined, right? Because, factorial, in this case, we're not even running any code. So we just run nothing. And if we're not returning anything explicitly, it's undefined all the time. So it'd just be undefined in this case. So Ranfi asks, if the number is negative, we would need another statement, right? You're thinking ahead. Yeah, we would, because you thought of a edge case here where basically if the number is negative, then it would not go into here, and it would go into here, and then it would keep calling. It would go an endless loop into the negatives, because it would just do -1 minus -2, and then it would call factorial -2, and that would call factorial -3, and there's no base case for that. So if you want to be really thorough, you would just say like, if num is less than 0, then return like -1, or return like this is not a valid factorial, because I don't think technically like you can even do factorials of negatives. So it'd be like, invalid factorial or something, or invalid operation. But you're thinking, I like how you're thinking about edge cases. That is a true statement, is if it was negative, then it would break the way it is right now. So here, see, like here, there's another example where we're just logging num times factorial num minus 1. Now this is close, because now we're actually logging 2 to the terminal, but the result is not going to be 2 because we're not returning. So we're just we're essentially just calling a function and returning nothing. And when we return nothing, they always give you the value of undefined. So what this will do is this will log 2, because 2 times factorial of num minus 1, and here we're returning 1, so factorial of 1 becomes interchanged with 1 once it's done running. And so then that becomes, we're doing console log 2 times 1, which is going to log 2. But we can't store that value anywhere because we're not returning. So it's 2 and then it's undefined. And how we actually do it is like this, and now we've returned. So now we could store the value of the function call within a variable. And it just works for all the other cases. And let's walk through how it handles the more complicated cases. So we call factorial 5, right? And it puts factorial 5 on the call stack. And it runs line 7, right? And line 7 is 5 times factorial 4. But we can't finish, we're not done with factorial 5, because factorial 5 hinges on factorial 4 being done. It depends on it. So does anyone want to take a stab at what happens next on the call stack? The next operation, exactly. Anderson, right on the ball, it puts factorial 4 on that call stack. Now factorial 4, much like factorial 5, along the same vein, it just runs line 7, because it can't run line 4 because the conditional is false. So it just runs line 7, and we get 4 times factorial 3, right? And now factorial 4 hinges on factorial 3. It's like, hey, until factorial 3 is done, like I can't do anything. I can't go anywhere because I need to know what this evaluates to. I need to know what factorial 3 evaluates to, and I don't know yet. So it's just going to keep that in memory, right? And it's going to say, I'll get back to you later. It's essentially like we could imagine, um, think about a movie theater. I actually picked this one up and I thought it was really easy to picture. But imagine you're in a movie theater and you're in some unknown row. So like there's like 30 rows in the movie theater, right? And you're like somewhere in the middle, but you're not quite sure what row you're in. So how you might solve this, let's say you want to figure out what row you're sitting in, right? And you don't want to get up and count. Like the iterative solution would be to get up and then count, like, okay, 1, 2, 3, 4, all the way until you get to 0, and that's your iterative solution, right? But your recursive solution, if you're sitting in a movie theater in some undefined row, or unknown row, is you ask the person in front of you, hey, what row are you sitting in? And then that person asks the person in front of him, like, hey, what row are you sitting in? And then it goes all the way till the first row, right? And the first row guy's like, dude, there's no one in front of me, so I'm in row 1. And then he tells the guy that asked him what row he's sitting in, I'm sitting in row 1. So that guy that got answered, he's like, I must be in row 2 because the guy in front of me just told me he's in row 1. And then the guy in row 2 turns around to row 3 and goes like, hey, I'm row 2. And then the guy that's in row 3 is like, oh, like, you're row 2? Well, I must be row 3. And then the guy that's in row 3 turns back around to row 4 and he says, I'm in row 3. And the row 4 guy's like, I must be row 4. So then he turns back around and it comes all the way back to you. And then you're like, I didn't have to do any work. Well, everyone else had to do work, but it's a different way of approaching it rather than counting each row. You just ask the person in front of it. So like, it's the same idea here. Factorial 5 is saying, you know, hey, factorial 4, what's your factorial? And factorial 4 is like, hey, factorial 3, what's your factorial? It's the same as like the movie theater row example. And we keep going, right? And in the movie theater example, the base case is when the row is 1. And the same thing here. You know, when we hit factorial 1, right, it doesn't call factorial anymore. It just returns 1 because it hits line 4 and we returned 1. And so now it gets popped off the stack, right? And it basically becomes 1 because it's returning 1. So it passes its value back to whoever called it, which is like the same thing as when the row 1 guy turns around to the row 2 guy and says, hey, I'm row 1. And the row 2 guy's like, thank you. Now I can call whoever called me and tell him, and now that guy can turn around to whoever asked him and tapped his shoulder, and then the chain reaction goes all the way back up to the original caller. And the original caller is factorial 5 in this case, whereas the original caller in the movie theater example is like you. You are the one that started the whole thing, so it eventually goes all the way to the base case, and then all the return values get bubbled back to you. So TFAS, when will we know when to use a loop or recursion? It depends. If you're finding that it's kind of whatever makes more sense, and I guess as you get familiar with recursion, it'll become more and more like second nature. But for certain things, like it's more useful for more advanced things like iterating through a tree or doing a depth first search of a binary search tree, for example. Like using a for loop is a little more complicated, but for the most part you could do either or, but you just have to know. It's not necessarily like, oh, like I'm going to use recursion here or I'm going to use for loops here. It's more like just understanding what recursion is, and being able to solve a problem recursively is just going to be helpful. not necessarily like, oh, like, should I use recursion here or should I use for loop here? It's whenever you're faced with that decision, you're probably just going to use whatever's makes more sense to you. But it would just be important to know how recursion works, because it just also tells you, not only does it show you a different way of thinking about how to solve problems, but it's also, you're learning about the call stack now and things like that. It helps to teach what's really going on in the internals when when you use recursion. So yeah, now two's done, right? Because two here in line 8, it returns 2, and so it's done running, and so 2 gets popped off, and factorial 2 becomes 2, and 3 gets popped off, factorial 3 becomes 6, factorial 4 gets popped off, factorial 4 becomes 24, and then factorial 5 is 5 times 24. So some takeaways: we always want to test our base cases and use the simplest inputs and outputs. So, for factorial, like, what's the factorial of 0? What's the factorial of 1? Let's test it out. Let's test out our function at least works for those simplest cases. So for the, just literally do this. Like, when you don't even have this, right? Literally just do this. And if there's a sum function, just literally sum the array of 1, length 1, and just return it, and at least know that you have the base case down. And the iterative case is going to be a little trickier, but I would always try to get those quick wins and solve the simplest case. So if we're trying to sum an array of length 1, right, and we got that down, then try to solve the array of length 2. And then work your way up to the longer ones before you just start tackling the long one right away. And then that's what these are saying basically, is use your simplest case and then test against more complicated inputs. You should try to use Chrome's debugger. It can help inspect recursive calls. Let me try that actually. So if we have, I'm not 100% sure. I don't know if I remember how to, let me see. Yeah, I might have to get back to you guys on how to use the debugger. I haven't used it in a while, so I'm not 100% sure how to use it. Let me see. Chrome debugger. Let's see. Let's Paint UI console. Get started. Run method. Yeah, I will get back to you guys on this. I'm not 100% sure. Yeah. But if we are having trouble with debugging a recursive function, I'm not sure why it says console log will not be useful with recursion. Let me try that. Function factorial num if num less than or equal to 1, return 1, else let result equals num times factorial num minus 1, return result. I don't know why I wouldn't work. Result. Factorial of 10. Go 2, 6, 4. Yeah, you could do something like this that still works. I guess why this happens is if technically, it could maybe overwhelm this terminal, but yeah, and it's always good to use a debugger. I just personally, it's a bad habit that I'll admit to, is I just use console logs, but it's there and it's a resource that we could all utilize. Yeah, I guess console logs, it can act weird. There could be weird edge cases, but I'm not too familiar with what that might be in this case, unless so if there was, what's that other common example? Fibonacci sequence or something. So if we were, I guess when console log wouldn't be as useful as if we were doing something like fib, I forgot, it's Fibonacci sequence again. 0, 1. Is series of numbers added by two numbers before it. So of num is if num is 0, then it's 0. If num is 1, then it's 1. Else return fib num minus 1 plus fib num minus 2. Right? So if you're doing like 2 recursive calls in the same line or something, then I think it could mess things up, or I mean, your output would just be really confusing because this is like a branch, like it represents a branching in your recursion. And so let me see, minus 2. Return result, console log result. Let's do fib of like 5, which should be, or I don't even know if I'm doing this right, but let me just try this out. Am I even doing this? Wait, the Fibonacci is a series of numbers. The next number is found by adding up the 2 numbers before it. So Fibonacci, the next Fibonacci of 5. Let me just see how it's solved. Fibonacci code. What the heck? F of n is f of n minus 1 plus f of n minus 2. What? But it's weird that Fibonacci of 5 equals 5. I guess it'll be different if it's not always going to be like, okay, cool. I was just, because it didn't make sense that it was just itself. So I guess I got confused by that. But like, for example, for this, it's console logging is not very helpful because it'd be really easy if I could draw this out. But essentially what happens is it branches out. So Fibonacci sequence tree. So this is what happens in the code. So Fibonacci 5 calls Fibonacci of 4. I mean, I thought Fibonacci 5 would call 4 and... Oh, I guess these are the actual numbers. These are the actual values. I mean, that's a little confusing, but this is kind of what happens is like Fibonacci 5 is Fibonacci 4 minus Fibonacci 3. And then Fibonacci 3 is minus, it all makes this tree-like structure. And so I guess console logs wouldn't be that helpful because we wouldn't really know where we are in this tree and it's not linear anymore. So that's maybe why, but I also don't see how debugging would help there. Maybe, I mean, it kind of would be better because you'd actually see all of the values and variables at that stage in time. So in this case, debugging would be better actually. Whereas console logs would just be like a huge mess because you can't really represent, it's not a linear operation. It's more like each level, it branches out into 2 more levels. So yeah, that is, so you can use recursion with any data type. Oh, so here are some quick patterns to note. When your input is a string or an array, usually the base case is when that string or array is empty or if it has a length of 1. So the sum example, right? If array of length is 1, the sum is just that element. Yeah, and also another pattern is like when the base case is that piece of data, the length is 1 or 0, that means that in every recursive case, we need to get it closer to the base case, right? So we need to somehow subtract from the size, like reduce the length of the array, reduce the size of the array as the input, or reduce the size of the string as the input. For nested arrays, we'll learn how to solve it in the next lecture. Again, always start with the base case. Always test with the most simplest thing. So like when we're trying to do when we're trying to solve factorial, always solve factorial of 0, and then solve factorial of 1, and then solve factorial of 2. Like work your way up in the simplest cases. And even if you find yourself like hard coding things, like it's better to do that and then think of how you could generalize it, but just first hard code it first and just try to figure out the solutions for the simplest cases. This is also something good to remember is that recursive case should always return the same data type as your base case. So for example, in this example right here, right? This is a number. This is also a number. So in your recursive case, it should also return a number because we're all aggregating in each level. We're always aggregating in this case. And so we shouldn't, return like a string here or something. We should always return a number. And this is going to be a number because it's, number plus a number is always going to be a number. But each level needs to be the same data type or else, when we're doing operations like addition or subtraction, like if all of the data types that are being passed back aren't the same, then we're going to end up like adding a number to a string or adding a number to undefined, and it's not going to work out in the way we want it. So at each level, we have to make sure the data type that we're returning is the same. They have to all be consistent throughout. yeah, that's pretty much it. It says to use console logs. You could also use a debugger for the more challenging ones. Um, I will get back to you guys on how to use the debugger. It can be really helpful, actually. Um, Again, base case and iterative case should always return the same data type. And if you're stuck, just try and, I would say before you try to do it iteratively, just try to start with the simplest case, the most trivial output. So let's say someone was like, oh, reverse string um, using recursion, right? Well, how would you, what's the reversed string of an empty string? Like, what if your input was an empty string? What would you return? Go even that simple first, right? And so if it's empty string, I'm just gonna return the same thing, right? And then what if your string was only one letter, like A? How would you reverse that using recursion? You just return it. You just return the same thing. Now let's get a little trickier and say, what if your string was AB? How would you get BA? Well, maybe you get, you use like string dot length minus one to get that last thing, and then you add it. You know what I mean? Like, it kind of, if you work from the really simple cases, you could kind of see a pattern, and usually you could generalize that to longer inputs. That's it.